Since we've already talked about logarithmic functions, next we're going to talk about exponential functions. And the reason they come one after the other in order here is that they're inverses of each other. So let's go ahead and look at exponential functions, logarithmic functions, graphs, domain, range, all of those good things, and then we'll apply some calculus to it. So y equals natural log x, of course, is a logarithmic function, and the inverse of the logarithmic function is this exponential function. They are inverses of each other. So e is the natural number e, and it's equal to about 2.718. So I'll make some notes about that in a moment. Let's go ahead and look at a graph. So we already know about the natural log. So if we had y equal natural log of x, and then I looked at my input and output, my domain and my range, the natural log of 1 would be 0, and the natural log of e would be 1. So let's go ahead and plot those points. So here's the natural log of 1 is 0, and then the natural log of e, and e is about, like I said, 2.78, so about here is 1. So this is the natural log, and we also know that there is a vertical asymptote through there. And so that's your natural log graph. Let's go ahead and look at the graph of e to the x as well. Now notice, because they are inverses of each other, the domain and the range swap. So the ordered pair 1, 0 becomes 0, 1 over here, and e1 becomes 1e. So let's plug that in and check. E to the 0, so if I plugged a 0 in, e to the 0 is equal to 1, e to the 1 equals e, so that makes sense. So here's that point 0, 1, and then the 1e would be 1 and then about 2.718. So this is your exponential growth function. This is what's used to calculate interest rate, growth, spread, all of those types of things. Now remember, because they're inverses of each other, they reflect across this y equal x line that bisects the first quadrant. And that's kind of what I have going on here. Now remember, you do have this vertical asymptote. It's not for the exponential function, it's for the logarithmic function. And then also we have a horizontal asymptote here for this axis for the exponential function. So those are some kind of interesting characteristics that we could talk about. Let's also talk about the domain and the range. So we have the function f of x, and we'll just write out the function e to the x, and we have natural log of x. And then let's talk about the domain and the range. Okay, so natural log of x we're sure about because we've already worked with this before. The domain is 0 to infinity. It cannot equal 0. And the range was negative infinity to positive infinity. Now remember, these swap. So up here, the domain of e to the x should be negative to positive infinity. So let's check that. Domain are x values, left to right. That's true. So as I keep plugging in values out here, I keep moving up here in this direction. And then my range would be 0 to infinity. So range is vertically, so it does look like that's correct. It starts just above 0 and goes off toward infinity. So the domain and the range swap just like we would expect. Let's go ahead and talk about a couple other quick characteristics here. We mentioned that e is approximately equal to 2.718. Okay, it's a natural number e. It's kind of like pi, irrational, non-terminating, non-repeating. Let's talk about some properties of exponents and properties of that exponential function. Okay. So first of all, if I multiply like bases, my shortcut rule is to add exponents. If I divide like bases, my shortcut rule is to subtract exponents. If I want to talk about a negative exponent, I could rewrite that with a positive exponent by reciprocating. And if I want to raise a power to a power, I multiply the powers. couple of other things that we've talked about. E to the 0 is 1, and e to the first is e. And this is another one that will come up quite a bit when we're evaluating functions. If I have a function e to the ln of x, I can just rewrite that as x. So again, this does come up. We could do a quick little proof of this. And the way that we would do that is we would set it equal to y and then take the natural log of both sides. So what this means is whatever this argument is here, you can think about, and this is not actually what's happening, but you could think about it as this base of e cancels with this base of e, because remember the natural log of e just means log base 10 of e. Okay, so natural log is log, I'm sorry, it's log base e of e, sorry. So natural log is log base e of e. So if you think about this base, you can think about that as an e, and you can see that it'll cancel. And this will show up quite a bit when we are starting to work with derivatives and integrals. So we have two big formulas here. We have the derivative and the integral. So the derivative of e to the u, and u could be any function in terms of x, is just e to the u prime. Now another way to say u prime is du dx. I like to say du dx. I think u prime, but a lot of times these prime marks get confused with firsts and then students miss them a lot. So I always like to write out the du dx just to make sure that everybody's clear on that. The next thing is the integral of e to the u is really easy to remember. The integral of e to the u du is e to the u, and then of course plus c if it's an indefinite integral. So these are the derivative and integral of the exponential function. Let's go ahead and start by practicing some derivatives. Now remember, the derivative is the slope of the tangent line. It still hasn't lost its definition. So this is the derivative of e to the 5x. So this is like e to the u. So the derivative of e to the u is e to the u times the derivative of u with respect to x in this particular case. The derivative of 5x is 5, so I would write this as 5e to the 5x. If we have the derivative with respect to x of, let's put a constant out front, or a coefficient out front, 3e to the x. We just drag the 3 along. It's not part of this problem really. And then the derivative of e to the u is e to the u times the derivative with respect to x is 1. So this is just 3e to the x. So the derivative of e to the x is e to the x. The only thing that changes is that argument is different than just an x. Let's look at the derivative with respect to x of e to the negative 2x plus 4. The derivative of e to the u is e to the u prime. Okay, so now we've got to finish it, e to the u, and then that u prime is the derivative of negative 2x plus 4 is negative 2, and then we could rewrite that as negative 2e to the negative 2x plus 4. So taking derivatives, just remember that derivative of e to the u is e to the u prime. U prime is the same as du dx. Let's take a look at the derivative, and of course we want to involve trig functions as much as possible. The derivative of e to the u is e to the u prime. So then I would take the derivative with respect to x of cosine of 2x. Okay, so that would be e cosine of 2x is my e to the u, and then my u prime, the derivative of the cosine of 2x is negative sine 2x, and then the derivative of 2x. That's the chain rule, doing lots of chains. Okay, so e to the cosine of 2x times a negative sine 2x. Now the derivative of 2x is 2. Now I can rewrite this as negative 2 e to the cosine of 2x sine 2x. Okay, and you have to be a little bit careful how you write this. Make sure you're using parentheses around the arguments of your trig functions. I think I've mentioned that before, but it is really important. Let's look at the derivative with respect to x of 1 plus 2x. times e to the negative 2x. Now, the way this is written, I could use the product rule here. I'd have the first times the derivative of the second. So I have two functions. So I could use the product rule, or another option would be to take this e to the negative 2x and distribute it here and here. I'm still going to have a product rule, but it might be a little bit easier of a product rule. So I think that that is the strategy I'm going to take. If you'd like to do another one, you could just use the product rule without distributing, and then we should be able to compare answers at the end. Now, our answers might not be identical. They might need to be simplified to be identical. So if I distribute this, I get e to the negative 2x plus 2x e to the negative 2x. And I'm going to take the derivative of everything here. So my derivative would be, the derivative of e to the u is e to the u prime. So negative 2x would be my next step. Now over here, I have this big old product rule. So here's my first function and here's my second. If you want to think about that as f and g. Now when I do my product rules, I always say a little saying to myself: first times the derivative of the second plus the second times the derivative of the first. So there's a couple ways you can think about that. Some people think fg prime plus f prime g. There's a lot of different ways to say it. So let's go ahead and keep working through it. The derivative of negative 2x is negative 2. The derivative right here is the derivative of e to the u again, which we just found. So that's going to be e to the u prime. So the derivative of e to the u is e to the u times the derivative of the argument, or the derivative of the exponent. So that is e to the negative 2x for my next step, and the derivative of 2x is just 2. Now, that's this derivative. This is the derivative here, but I'd still need to do some more simplifications. So let's go ahead and write that out. So I get e to the negative 2x times negative 2 plus 2x e to the negative 2x. And then the derivative of negative 2x is negative 2. Okay, so now I have a lot of rewriting and simplification I want to do here. I'll pull that negative 2 out front. Whoops, I got a 4 there and a negative. Let's pull that out. So I have a 2 and a negative 2. That would give me a negative 4 x e to the negative 2x. And then my last term is plus 2e to the negative 2x. So these cancel with each other, and I'm left with negative 4x e to the negative 2x. Okay, negative 4x e to the negative 2x. Let's look at a problem that it looks kind of complicated actually. There's a lot going on here. This is theta cubed, e to the negative 2 theta, so there's my exponential, and a trig. It's got everything. Now when I look at this, thinking ahead for derivatives, this is a double product rule. So I could use this as my first and this as my second, or I could use just this one as my first and this as my second. So there's a lot of things going on here. But I think this will be a great opportunity to try my logarithmic differentiation. Because if I can simplify this first, it will make my derivative a lot easier to take. Fewer things to keep track of. So to get started with logarithmic differentiation, the first thing I do is I set this equal to y. And then what I'll do is take the natural log of both sides. So I have the natural log of y equals natural log of everything on the right. And remember, please put parentheses around the arguments of your trig functions. Thank you. And then I'll distribute the natural log. I shouldn't say distribute the natural log. What we're doing is this is the log of a product as the sum of the logs. So this is the natural log of theta cubed, okay, plus natural log of e to the negative 2 theta plus natural log of cosine of 5 theta. Okay, now there's a couple things I could do to simplify this first. So again, I have the natural log of y. Now this 3 right here I can pull out front. So that's going to be 3 natural log of theta minus 2 theta natural log of e. Now the rule that I used there was that power rule, meaning I can pull that exponent out front. So I can pull this out front, pull this out front. Now the nice thing about this is the natural log of e is 1. So when I rewrite this, I have the natural log of y equals 3 ln of theta minus 2 theta plus the ln of the cosine of 5 theta. We still haven't taken the derivative. We're just simplifying. We're preparing it to have the derivative taken. And this pre-work that we do will actually make taking the derivative a little bit easier. So now let's take the derivative. The derivative of the natural log of y is 1 over y prime, or dy dx. So here, the derivative of the natural log theta is 1 over theta times the derivative of theta. And I know that's 1, but I want to write it in. The derivative of minus 2 theta is minus 2. And the derivative of natural log of cosine of theta is 1 over cosine of 5 theta times the derivative with respect to theta of the cosine of 5 theta, 1 over u prime. So the next step, we'll actually go through and take those derivatives. Okay, so I have 3 over theta, that's right here, and the derivative of theta with respect to theta is just 1. Now over here, I'm going to have 1 over cosine 5 theta. Derivative of cosine 5 theta is negative sine of 5 theta times the derivative with respect to theta of 5 theta. There's that chain again. Got to make sure you chain it back. This is like a double linked chain. So we've got our derivative almost. So that's 3 over theta minus 2. Now I'm going to simplify this a bit while we're here. This is going to be minus tangent. Sine over cosine is minus tangent 5 theta. And then the derivative of this piece right here is equal to 5. Okay, so that comes right down here. Now, that is the derivative right-hand side, but I'm not done yet because on the left-hand side, I just want dy d theta, or it should be dy d theta. I'll go back and fix that. So we're going to have to multiply both sides through by y to clear that. So here they'll cancel, and I'll be left with dy d theta is equal to y, and my original function y was theta cubed e to the negative 2 theta times cosine of 5 theta. So that came, this y I'm putting out front. Okay, and then I have 3 over theta minus 2 minus 5 tan 5 theta. Okay, and that's my answer. It's not a very pretty one, but that is it. Okay, I'm going to hit pause and scoot back and change those dy dx's to dy d thetas. So that's a look at taking some derivatives. Actually, I think there's one more derivative I want to look at. Oh, I guess go on to integration. Okay, so let's look at the integral of e to the 3x dx. So to get started on this one, we would use u substitution. So I'd let u equal 3x. du would then be 3 dx. I'm missing the 3. So what I do is I end up setting this integral of multiplying by 3 on the inside, compensate with a 1/3 on the outside. And then rewriting, I have 1/3 integral. And then this is e to the u, this is e to the u right here. And then the 3 dx becomes my du. Okay, so this is my e to the u du. Okay, so this is 1/3. The integral of e to the u is e to the u. And then I sub back in. U in this case was 3x, and then plus c, my constant of integration, because this is an indefinite integral. Okay, let's look at another one. Let's look at e to the negative 2x plus 5e to the negative x dx. Now in this particular situation, when I look at the exponents, I see right away that they're different. And because they're different, I'm going to split this into two separate integrals. So my first integral is going to be the integral of e to the negative 2x dx. And my next one will be plus 5. I'll pull that 5 out front so I can focus on the integrand negative x dx. Now the reason I split these up is the arguments are different, so my substitutions are different. So here u would equal negative 2x. du would be a negative 2 dx. I'm missing the negative 2, so I multiply by negative 2 on the inside, compensate with a negative 1/2 on the outside, and this ends up looking like negative 1/2 integral e to the u du. Now over here on my next step, my argument, I'm not going to use a u, I'm going to use a w, because if I use a u, I've already defined that for this problem, so I need to use a different variable. So if w for my substitution is equal to a negative x, dw is equal to negative dx. Okay, so here this would be 5 integral e to the u, but I don't have the dw. I need the dw. And this should be w right here. So the e to the w, I don't have the dw. I'm missing a negative on the inside and a negative on the outside. And now this negative dx right here becomes my dw. Okay, so integrating over here, the integral of e to the u is e to the u. And over here, my integral of e to the w is e to the w. And these are added together. And then I do my substitutions. And then, so this is why I have to use two different variables for my substitution, because if I used u for each of them, what would end up happening is I'd sub in the wrong thing for this second one, which is just negative x plus c. Now this could be simplified a little bit. In fact, yeah, I think we should. Let's simplify it. The reason we're going to simplify it, first, it's fun, and second of all, at some point we're going to be evaluating these expressions, and they're easier to evaluate when they're simplified. So I think the first thing I'd like to do is think about a common denominator, which would be 2, so I'd multiply top and bottom here by 2. And then right away I see I have a negative 1/2 that I could pull out, and I also have an e to the negative x that I could pull out. So when I factor out a negative 1/2 e to the negative x out of here, I have to think about what is my remaining factor, and the remaining factor is e to the 2 here. And if you're not sure, multiply back through. E to the negative x times e to the second is e to the negative 2x. Okay, I already pulled out the negative, so I'm going to be left with a positive 5 plus c. Now the reason it's just a positive 5 is I've already pulled out all of this, so the only remaining factor is the 5 here. We'll do a little bit more rewriting. So this would be equal to e squared plus 5. The denominator would be 2e to the x when I flip that down. And then there's a negative sign here, and that negative sign I can either put it out front, or I could have something like minus e squared minus 5 all over 2e to the x. What you don't want to do is write it something like this, where you stick the negative like this, because what ends up happening it looks like just the e is squared is negative, and it has to be the whole thing. So do not write it like this. So having said all this, these are some fine answers right here before we simplified, and then after we simplified, these are good as well. Now you can see by looking at these, this is a little bit complicated, but when we get to here or here, this would be easy to evaluate. So that's one reason for simplifying. Now this integral we've actually looked at before, or close to it. Let's look at e to the negative x, but this is going to be a definite integral, and I'm going to go from minus ln of 2 all the way to 0. So use our u substitution. U is equal to negative x. Du is a negative dx, so I'm going to multiply by a negative on the inside and the outside to compensate, because a negative times a negative is a positive, and I haven't changed the value of this function. And notice I dropped my limits of integration. I could change them if I wanted to in terms of u, but I just chose to drop them. We'll put them back in at the end. So when I rewrite this, I have a negative sign, and then I have my negative dx becomes my du, and e to the negative x becomes e to the u. So the integral of e to the u is e to the u. I switch back to my variable x. U is negative x from up here. And I'm going to evaluate this from negative natural log of 2 to 0. So if I wanted to, I could rewrite this first. I could flip it and then evaluate it, or I can evaluate it with the negative exponent, whichever works better for you. So I have minus 1 over e to the 0 is my upper, and then my lower would be negative 1 over e to the minus ln of 2. Okay, let's simplify. E to the 0 is 1, so this is negative 1 over 1. And then a negative times a negative is a positive 1. E to the negative ln of 2. I'm going to leave that right here for now. And let's rewrite that again. So negative 1 over 1 is negative 1. Now, because that negative is in the exponent, I can flip that up top just like this. Now remember, we had this rule. So we had this rule at the beginning here. If we had, let me scroll back up. It's a ways back. It was right on the front page. We had this rule right here. Where is it? I thought it was one of the properties. Oh, here it is. Right here. E to the ln of x equals x. That's what we're going to grab. So e to the ln of x equals x. So e to the ln of x equals x. So e to the ln of 2 just equals 2. Negative 1 plus 2 is 1. So that whole integral, all this work just to find the number 1. Isn't that nice? Came out really good. Now, the thing to remember here is that the base and the log base here are the same. So again, they don't cancel each other out, but it's a way that you could think about it to help you remember. Okay, we're moving right along here. Let's go ahead and look at another example. The more examples we work, the better, just because you'll get more and more familiar with these integrals and know what to expect for substitutions from them. So this one, our u substitution would be the exponent, x over 4, and the du would be 1/4 dx. Okay, so I have the dx, I need the 1/4, so I'm going to multiply by a 1/4 on the inside, compensate with a 1/4 on the outside. The overall effect is multiplying by 1, and again I drop my limits of integration. So I have e to the x over 4 is e to the u, and then 1/4 dx is du. Drag the 4 along, the integral of e to the u is e to the u. Then I change back to my original variable. U was x over 4, and now I'll evaluate this from 0 to ln of 16. So I'm going to leave my, well no, I'm going to drag my 4 along. So this would be the ln of 16 over 4 minus my lower 4e to the 0 over 4. So remember that 1/4 that's out front right here, I'm probably going to pop into the exponent, but I'll just rewrite it for now. 0 divided by 4 is 0. So this is ln of 16 to the 1/4. And then e to the 0 is 1, so this is minus 4. Now the interesting thing here is 16 to the 1/4. 1/4 is 1/2 times 1/2, so that means taking the square root twice. So square root of 16 is 4, square root of 4 is 2. So I can rewrite that as ln of 2. Now remember this e to the ln of 2 bit, that just simplifies to 2. So this would be 4 times 2 minus 4. 8 minus 4 is 4. So that was a neat simplification. Again, we use that rule again. E to the ln of 2, think about those ln's and the e's canceling, and you're left with 2. Let's look at another integral. e to the square root of r over the square root of r dr. Now again, it's trial and error, so you have to try something here. So we have a nice integral for e to the u, so let's let u equal that exponent and see how that goes. Now to find du, it would be helpful if this r was written as r to the 1/2 instead of square root of r. Now when I find my derivative, I bring the 1/2 down, decrease the exponent by 1 dr. That negative exponent I can flip, and it ends up with 2 root r into the denominator, which I almost have. So let's look and see what this looks like after compensation for the missing coefficient. So I need a 2 down here in the denominator, so I have to compensate with a 2 up here in the numerator. So when I rewrite that, this is equal to 2 integral e to the u, and then 1 over 2 root r dr would be my du. So the integral of e to the u is e to the u. U is square root of r plus c. So a nice straightforward little u substitution using our new function and our new formula. Okay, let's get into some little bit more complicated ones. Let's look at the integral of e squared. So what are your thoughts on this one? Well, this one's a bit of a trick. So a lot of times you look at this and you just go for the exponent and you don't really think about what's going on here. But e squared is a constant. Remember, e is the number approximately equal to 2.718. So e squared is just a constant. So this is actually just the integral of the constant times dx. So if we pull that constant out front, I'm left with 1 dx, and the integral of 1 dx is x. So this is equal to e squared x plus c. So that was a bit of a trick. So look at what it's saying. Variable, what is the variable? What is the base? Okay. Another thing a lot of people do for this one is don't do this. A lot of people take this and go, oh, I'll add 1, divide by the sum, and I'll get e cubed over 3. That does not work because our base is not a variable. The power rule that we learned in Calc 1 only works for things like x squared, x cubed, things like that where the base is a variable. Here our base is a constant, so I can't do this. So don't do that. Okay, let's look at another one. Let's look at the integral of 2t e to the negative t squared dt. Okay. So again, let's go with the u to be the exponent to see what happens. Du is negative 2t dt, and I have that. So I can multiply by negative inside, compensate with the negative on the outside, and I have negative integral, okay, e to the u, and then du. Okay, so integrating, the integral of e to the u is e to the u, and I make that substitution back that u equals negative t squared and plus c. So you have to make sure you compensate on this one. Let's get some trig in here. It's been too long without a trig problem. Okay, 0 to pi over 4. This is going to be 1 plus e to the tan theta times secant squared theta d theta. Okay, so I'm going to go for what we would typically do. We'd look at that exponent and we'd let u equal tan theta. Du, the derivative of tangent is secant squared. And we'd look at this and we'd say, okay, I've taken care of this and I've taken care of this. I've not taken care of that. So the substitution I chose will not work because I have that 1 left over. So this doesn't work. Okay, so let's try 1 plus e to the tan theta. So let's try u equal 1 plus e to the tan theta. Derivative of 1 is 0. Derivative of e to the tan theta, the derivative of e to the u is e to the u prime. Derivative of tangent is secant squared theta d theta. Don't have it. So the problem there is I've taken care of this bit now, and I have this, but I don't have that, and I can't compensate for it. So this doesn't work either. Okay, so we have to come up with something else. I think what we should try is to take this and distribute through and get rid of that binomial times a monomial. So let's go ahead and rewrite it to see if that gets us anywhere. So if I take secant squared and distribute it, I'd end up with just secant squared plus e to the tan theta secant squared theta d theta. Okay, this looks good. Okay, so I'm going to split this up into two separate integrals. And the reason I'm going to do that is I'm going to have two different techniques. So I don't want the different techniques to get confused. Okay, now this is real nice. This is just an antiderivative. So the derivative of tangent is secant squared, therefore the integral of secant squared is tangent. So this is just tangent theta. Now over here though, I'm going to go back to my u to be tan theta that I did up here, but I think it will work now because I got rid of this one piece that was not being taken care of. Du, derivative of tangent, is secant squared theta d theta. Okay, so when I rewrite that one, that's going to look like the integral of e to the u du, which integrates to e to the u, which is just e to the tan theta. So that worked good. Okay, so now let's try and regroup here. Kind of have a little mess going on. So I have this tan theta from this piece. And then I have this e to the tan theta from this piece. And I need to evaluate this from 0 to pi over 4. Okay, so we'll do our upper and lower. So tangent pi over 4 plus e to the tan pi over 4. Make sure we know that unit circle. And then our lower would be tan 0 plus e to the tan 0. So the tangent of pi over 4 is 1. Tangent of pi over 4 is 1. So this is e to the first minus tangent of 0 is 0 minus, because I'm going to take this and distribute it, tangent of 0 is 1. So writing this out, I get 1 plus e minus e is, these cancel, and I'm left with 1. That actually doesn't look right. Let me take a look at that. I feel like it should be not 1. Okay. Oh, I see it. It's right here. So tangent of 0 is 0. So tangent of 0 came from right here. So that term would be e to the 0, which is a 1, but that's negative out front. So 1 plus e minus 1, it's the 1's that cancel, and this is equal to e. That makes more sense. There we go. Okay, let's look at another one. Now, if we're given a function to integrate, if we know our power rule, product rule, quotient rule, log diff, we can differentiate just about anything. Integration doesn't really work like that. For instance, this particular problem, there's a lot of things we can't integrate, but this particular problem, we'd let u equal x squared, and then du would be 2x dx. Well, I can do something about the missing 2, but I can't do anything about the missing x. So this doesn't work. And I cannot integrate this yet. This is a Calc 3 problem. So we can't integrate it this semester, but next semester we might have a shot at it. Let's look at another one. Let's go dx over 1 plus e to the x. And of course I'm going to rewrite this. I like to be able to pull this dx out so I can focus on this integrand. So if we let u equal 1 plus e to the x here, du would be 0 plus e to the x dx, and I don't have that. And I can't just multiply something or divide by something with e to the x. I have to pull it out as well, and I can't do that with anything that has a variable. I can only do that with a constant. So this does not work. So we're going to do a little algebra trick. We are going to do divide through by e to the x every term. So 1 over e to the x, 1 over e to the x, plus e to the x over e to the x dx. So rewriting this, 1 over e to the x is e to the negative x. So that just means to take this and flip it up top. 1 over e to the x is e to the negative x. And then e to the x over e to the x is 1. Now you might say, well, what good did that do? Well, what it did is it created a dx for me. So I didn't change the value of the expression at all. I just rewrote it. So let's look at u to be negative x plus 1. And now my du is negative e to the negative x dx. So from here, I can see that I have my du right here now. I'm just missing the negative sign. So I'm going to compensate with a negative on the inside and on the outside. And I'll be left with negative integral 1 over u du. Natural log. So this is minus natural log absolute value of u. And we know u is e to the negative x plus 1 plus c. There's my solution. But I see a negative exponent, so I kind of feel compelled to simplify this a little bit more. It's not required. So e to the negative x is 1 over e to the x plus 1. Find a common denominator of e to the x over e to the x. And then, this is fun. I'm glad we did this. Okay, so now this negative that's out front, I'll rewrite this real quick, all over e to the x. This negative that's out front, I can pop it up top, and that becomes a negative 1. Now remember, it's to all of this. And the effect of the negative exponent is to flip everything around. So this is going to be e to the x over 1 plus e to the x plus c. So there's another solution. It's exactly, if we were to graph this, they'd be exactly the same. Okay, they're only off by a rewrite. So kind of an algebraic simplification. Okay. Let's look at, this is a nice one. Let's look at e to the 1 over x all over x squared. This one is easy to miss just because we don't often catch ourselves looking at that derivative of 1 over x right away. So let's look at 1 over x for my u. If I rewrote that as x to the negative 1, very quickly I'd see that du is negative x to the negative 2 then, which is negative 1 over x squared dx. That's this. Okay, so from here I can see that I'm missing the negative, so I multiply by a negative on the inside, compensate with a negative on the outside, and here we go. So I have negative on the outside now. So e to the 1 over x is e to the u, and then negative 1 over x squared dx is my du. So the integral of e to the u is e to the u. U is equal to 1 over x plus c, my constant of integration. Now you could also see this rewritten as negative e to the x to the negative 1 plus c, because remember 1 over x, I could rewrite that as x to the negative 1, but I think that this will be kind of more of the more common way to see that. Okay, I think we have time for a trig. We'll end up on a trig, one of my favorite things. Let's end up with something good here. Let's look at some trig. Let's look at the integral of e. Let's do a secant. Let's see if we remember our trig derivatives. E to the secant pi t times secant pi t tangent pi t. And of course dt. Now when we see the e right away, what you should start with, and again it might not work the first time, but we should start with letting u equal that exponent. So let's let u equal secant pi t, and then du, the derivative, okay, this is why I got to remember our derivatives. So the derivative of secant is secant tangent times the derivative of the argument. So secant u, tangent u, u prime. So this is secant pi t, tangent pi t, times the derivative of pi t. I just want to include that step for you. So the derivative of pi t is just going to be pi. If it was 3t, it would be 3, but pi is just your constant here, so this is just equal to pi. So I'm going to pull that pi out front, and then I have secant pi t, tangent pi t. So let's see what we have here. I have everything I need. This is my du. The only thing I'm missing is this pi. So I can multiply by a pi on the inside, compensate with the 1 over pi on the outside. So let's look at 1 over pi. And then this is going to be e to the u du. Wow. Doesn't that look a lot nicer? All of this replaced by just this. And of course, once I have that, the integral of e to the u is e to the u. In this case, u is equal to secant pi t plus c, my constant of integration. That was a good one. That was a good one to end on. I'm only sorry that I didn't put limits of integration on that, because that would be fun to evaluate. Okay, so as usual, if you have any questions, please let me know. I'm happy to help. You can send me a screenshot of your work. You can message it to me and remind. You can stop by during my office hours. You can either join online or on campus, and of course the slide rule is open. We also have the free 24/7 tutor that you can access through D2L. If you go to D2L Help and then choose sdsmttutor.com, that's another way that you can access some help. So we're here to help. If you have your formulas and very carefully step through them, it's going to be hard first. It's kind of be like grinding gears, but as soon as you start getting more and more of these done, it's going to start running smoother and smoother, and you're going to start seeing some of these patterns and things that you should be able to choose for your UDUs that'll work the first time. So don't get discouraged, just keep putting in that effort, ask for help when you need it, and we will help you out with this. Hope this goes well, hope you enjoy it. I think it's kind of fun. I really like doing these problems with you, and if you have any questions, let me know. Good luck.